Okay, I want to start 11.3 by explaining the idea behind the chapter, which is a really important concept for coming to grips with what an infinite series really is. So you may remember that we defined an infinite series and its sum in analogy with how we defined an improper integrals calculation through a limit, right? So this is actually much more than an analogy. We can actually think of every infinite series as an improper integral so that the two definitions are exactly equivalent. So in other words, I could have defined infinite series as nothing more than a specific type of improper integral. So let's imagine that we have infinite series, sum from k equals 1 to infinity. So I'm going to use k as my index here for the terms. So a1, a2, a3, and so on. And let's define a function to go along with this infinite series in the following way. So let's call it f of x. So it's going to be defined on the interval from 1 out to infinity. And we're going to define it to be a specific value of a sequence term, okay? The way we calculate it is, so if I plug in, for instance, x equals 5.5 in here, then I round down. This is called the floor function, by the way. I round down, and the value of f of 5.5 would be a sub 5, okay? The value of f of 6.1 would be a sub 6. Okay, so I'm always rounding down here, called the floor function. More specifically, it's not rounding down, it's the greatest integer, which is less than the number that we have. So I can show you the definition over here, actually. It's precisely the greatest integer m, which is still less than or equal to this. So the reason I say it's not rounding down is because it looks a little different for negative numbers, but it's not important for us because we're only talking about positive numbers here. Okay, so the important thing is that we're starting with a series and we're going to make a function that is basically mimicking the series. So here's the function that we would get, for instance, if I wanted to think about what is f of 1.5, okay? So I plug in 1.5 into my function down here on the x-axis, and the value I get out would be a sub 1. So you can see if I were actually plotting the sequence terms, like we're familiar with plotting a sequence, then I would plot 1, a sub 1 right there, for instance. A sub 2 would go with, for instance, this point, 2 comma a sub 2, 3 here, and so on. But my function, the function I'm actually graphing, say I highlight it in red here, and let's put y equals f of x on this graph. That would be all this. It goes here to here, and then it jumps down to here, and then it goes here to here, and then it jumps down to here. So it's a discontinuous function, okay? But it's a discontinuous function that's very closely mimicking what the series terms are doing. And if you think even a little bit more detail about what's going on with the shaded area under the curve, then you realize that the regions, or these rectangles that I've got, actually have areas that correspond to the sequence of terms. The area of this rectangle is its width times its height, and its height is a1. So the area is actually a1 in here. Here we have an area of a2 in this rectangle. Here we have an area of a3 in this rectangle. So you see that actually, if I were to sum up the all the terms of my infinite series, taking the limit as we add more and more terms, then we're actually doing the exact same thing as adding up area under this curve. So in fact, here is what we can say, that the sum of my infinite series, the one we started with, by definition is the limit of the partial sums, right? So I haven't done anything special there. That's just our normal definition. But each one of the partial sums right here, for instance, how about I think about what n is, let's say n is equal to 6, for example, right here, okay, then I would shade in all this right here. And that would be, for instance, my shaded area would be the partial sum from k equals 1 up to n equals 6 here of these terms, okay? But you can also calculate that area, not just by adding up A1, A2, A3, A4, and so on. You can also calculate it by doing the integral under the function that is the red curve that I defined here using the floor function, okay? And so you see we have a limit now of a definite integral from 1 out to n, and the limit as we go to infinity is an improper integral. So every infinite series can be thought of as an improper integral, okay? So that's the important idea that's going to allow us to leverage our understanding of improper integrals to learn about infinite series, okay? We're going to leverage our understanding of improper integrals to learn about infinite series. So let's see how we might do that. Give you a little graphical demonstration here in Desmos. So here I have a curve, an f of x, okay? And what we can do is add up with the area under the curve. That is a improper integral, right? So if I add up all the area under the curve out to infinity, that's an improper integral there, okay? Now, however, there is also a series that goes along with this function, okay? So just like we looked a minute ago, here's a infinite series that I am calculating this way. A1 for this series is just going to be the value f of 1. A2 for this series will just be the value f of 2. A3 for this series will be the value f of 3, and so on. And if I think of the series as an actual function, the one defined by the floor function like we had before, then look at what's going on. As I add up my infinite series there, I get this area, the blue area here, under this function, right? So discontinuous function right here, the function is going, and then it jumps down. Okay, that's the same idea that just introduced a moment ago. So I'm thinking of a series as a function now. And think about what we know happens, for instance, for the integral here, our green, the area under our green curve. So this, if I calculated the integral for this guy from 1 out to infinity, this would be an integral of the power function, right? And the power right now is sitting at 0.9. So that's a p-value that's less than 1. So what we learned about improper integrals is that there's actually an infinite amount of area in the green region here, okay? So what do you think that says about the blue region? My green region is infinite, has an infinite amount of area. So my blue region here, which is above it, must also have an infinite amount of area. And that means that the series that describes this blue region must diverge, okay? So I can actually say right now that just by this picture, we have proved that the sum of 1 over n to the 0.9 power from n equals 1 to infinity diverges. That infinite series diverges.